Yeah, I think we have done this much part. Okay, so we say DFAM can be solved using a half circuit method, and the condition we said that the system should be symmetric across some vertical line, and then left side and right side can be independently handled. Okay, and we had shown last time some theorem which is given in Razavi's book, and using the same method and across this there is a symmetry. Please remember here one of the thing I assumed that it is a differential system. What did I say? Vn1 Vn2 are such that one rises by delta, the other decreases by delta, but this is not really a condition. We will prove that this is not necessary, but initially we assumed that that should be necessary part. Now I will show you that is not really necessary, but first let us see if it is assumed that typically this op amp can be converted into half parts, and you solve output voltage at this by a simple amplifier minus GM1 RD parallel R01. Similarly you do for the other side, which is Vy by minus delta Vn1, which is Vy upon this minus GM2 RD1 RD2, and if I subtract or add whatever it is, I will get GM1 RD1 parallel R01. Now this idea that AV dash 0 which is essentially when I say RO equal to RO2 is equal to RD1 equal to RD2, GM1 is equal to, can be reduced to 2 GM RD, and RDs are smaller normally than R0, then it is same 2 GM RO, nothing very great appears. Okay, we can do it analysis which is much more rigorous, which we have been doing all the time. So there is a second method which I am not showing you, read from the Razavi's book, which is actually a circuit technique. What essentially they will do, for example, they will assume that one of the input is grounded Vn2, and then see the performance influence of Vn1 on Vo1 and Vo2. Okay, then they will figure it out what is the Vn1 is 0, and then they superpose the results to get the net gains. Okay, so that is a very standard technique of superpositions. So read that other technique which is more popular circuit technique. This was shown to you because DFAM shows symmetry, and therefore it is much easier to solve this method. It is not that this is the method or something, but if you see something simpler you probably go through it. Please remember in that case if you are using this will be driving this, so some kind of a source follower outputs are given to the common gate or common source system, vice versa, and then you have to do some real analysis to get the normal analysis done, which probably you can read. In case some of you did not find that okay or not understood, come to me individually, I will solve for it. Okay, that is nothing very big, but this method I liked it very much because for a DFAM case at least this is very good and simple. Yeah, in the region of VO Vn circuit is linear, devices are in saturation. Okay, you are right. However, there is an issue if you are looking difference gain as Vo1 minus Vn2 upon Vn1 minus Vn2, which is called AV difference mode, then this will become GM RD parallel R0, that 2 will go away, that is the only thing. However, the point which we actually took care in all our definitions so far, we said the Vn1 Vn2 are such that they are differential. What does that mean? We said if one changes by plus delta Vn, the other must go down by delta, but that is not very necessary, as I show you later. Okay, this is a good condition to start with, and we still say it can be still doable even if they are not fully different. We can see that a Vn1 can be broken into Vn1 by 2 plus Vn1 by 2, then we can add half Vn2 by 2 and subtract half Vn by 2 in series, power supply 4 in series, such that Vn2 cancels otherwise and Vn1 adds. So this is still Vn1, is that okay? Vn12 Vn12 they are in series, so Vn1. This is opposite, Vn2 are opposite in polarities equal, so they cancel. So this can be written as 4 supply in series Vn by 2 plus Vn by 2 minus Vn by 2 plus Vn by 2, keep doing this any number if you have this. Now this is 4, similarly I can say if this is so that I can write then I Vn1 plus Vn2 by 2 and Vn1 minus Vn2 by 2. So the statement that this can be represented by 2 such series power supplies or supplies or signal supplies. Now you can see from here what is this value could be looking for Vn1 plus Vn2 by 2. It is defined as common mode voltage, which essentially can occur because if Vn1 is equal to Vn2, so Vn1 plus Vn2 by 2 is Vn1, so it is essentially saying it is a common mode voltage, whereas subtraction is difference. So any signal therefore can be represented as common mode signal plus difference mode signal, because at the end why I said diffams, what is the important characteristic of a diffam, that it rejects all common mode signals as much as possible. So now we are representing this into series combination of common mode signal and this. Similarly I can do it for Vn2 on the other side, okay, and I am not saying it should be this, so I repeat this, is that okay? Okay, so equivalent is saying I have a 2 sources in something like this, and only thing is you can see here Vn2 minus Vn1, here Vn1 minus Vn2, because that is what the values you had, and correspondingly you wrote this. And then we define, as I say, a common mode voltage Vcm is Vn1 by Vn2 and difference mode signal is Vn1 minus Vn2, is that okay? So this representation of the, so now I am not saying that it goes delta this, I am not saying, I say whichever it is I will break into equivalently this, which will always give me some common mode signal and some difference mode signal, okay. Now the idea behind all this game was that what is the gain for this and what is the gain for Vc this, since there are 2 sources now, okay. So we say what is the method we will use, we will figure out the gain for difference and we are get the gain for common mode and check it whether one is much higher than the other or vice versa, whatever happens we will see what is. And if it so happens that the, of course there is another term which you should know, there is called common mode gain converted to differential mode, so it is called AVCM dash DM, okay, which we will calculate, okay. Is that okay? This is only a definition, everyone knows for last so many years, I have not figured out anything, I haven't got anything great new things in this. I repeat, I just broken the signals into common mode and difference mode signals. You can see this is plus Vid by 2, this is minus Vid by 2, Vcm is same, that makes my job much easier, because if Vcm is same on both cases then the circuit will become even simpler. So I have now 2 signals, one is plus Vid2 minus Vid for the difference mode, and for the common mode I have another equivalent circuit which says where it is common to both Vc, V and Cm, individually putting is as much saying common to both, okay. So I have 2 circuit to solve, and if I can solve these 2 circuits then we know, just now we did, Vx is minus Gm1 Rd parallel Ro1 into Vid by 2 at this point output, just now we calculated. The other side is Vy Gm2, this is, since it is minus Vid by 2 I put this plus, so it becomes Gm2 Rd parallel Ro2 Vid by 2. So I calculate difference gain which is Vx minus Vy divided by Vid, okay. So which is nothing but Gm1 and let us say Gm1 is Gm2 equal to Gm and Ro1 equal to Ro2 is R0. What does that mean? The 2 transistors are identical. We will get rid of this also and say if they are not, what will happen, okay. So if they are identical, the gain becomes just GMRD, which we just now calculated, that nothing great happens. However, if you look at for this second circuit and do similar analysis, Vx minus Vi, this gives me, since Vx is equal to Vy, then both input will give same voltages, okay, outputs. So the difference being 0, the gain is 0. So if I now take a ratio of AVDM to AVCM, it is infinite. That means at no time common mode signal will actually get amplified, okay. Is that okay? This is what essentially is the main feature of differential amplifier. The assumption in all this was, I repeatedly say that why this cancellation we said is important, because in real life one believes these two transistors will not be too far, they may be two input signal lines or sometimes one ground and one other line, in which case the noise may not over put separately for different places. So assumption is if noise sits on this something, same noise will put something on this, and if that happens the common mode noise will actually get rejected, okay. So that is the feature these diffams provide. So wherever you are looking for rejection of noise, you better try with a differential amplifier system in which you can reject common modes. Of course in real life we know VCM is not 0, okay, it is some finite quantity. So the ratio of AVDM to AVCM is not infinite, but large enough in finite numbers, and that value we will call it as common mode rejection ratio. Slightly different way we will explain that, but that is what we are looking for. Is that okay? So what is the diffam property? It will only amplify differential signals but not amplify, or actually will not amplify anything, or output will go to zeros difference if they are common modes. Please remember individually you will still can get outputs single stage kinds, but difference of them is 0. Please remember Vx is same as Vy, it does not mean Vx is 0 and Vy is 0. Is that okay? So this issue has to be clear, that transistor is amplifying, it is not leaving its job, still amplifying, but both sides being identical, outputs reach identical, and therefore the difference of the two is 0, okay. That is the reason why we say it is rejected. So if you only pick up output here, say oh there is a noise reading, yeah, noise is riding on it, okay, an amplified noise is riding on it in fact, okay, but the other side is also riding the same way. So if I take difference, the common part will cancel, and that is how we say noise gets cancelled. So please remember that if I make sometime wrong statement, which you are very smart to catch immediately, what I again say that I am never saying that Vx is 0 or Vy is 0, I am saying Vx and Vy are equal, okay. That is the statement I make. Even if there is some issue, please come back. Is that okay? These issues are actually all of you have done this earlier, I am just trying to see how do we use them in diffam design. Today of course we will not be able to design, we are going to design a diffam at the end, and there are certain other parameters of interest other than CMRR. One of course is the difference gain, how much you have. The other is we will like to know what is the common mode gain you get in reality, and we also will like to have more specification for a given diffam. Two of the specification maybe I will tell you today. One is called output swing. At the end of the day how much output is available to you from minimum to maximum is very crucial for the next stage, okay. Therefore I will like to know what is the output swing, and the most important among them is what is the possibility of device remain in saturation for any kind of VID, that is minus or plus. So the what is the minimum and maximum input which is possible for keeping devices in saturation, this is called input common mode range, ICMR. So these two, the another two more parameters which we will look into later, not today possibly, is the power dissipation, because for any design that may finally limit all your performance. If I say this is 1 milliwatt, that means and VDD is so much, the maximum current given to you is so much, IDD into VDD is the power, okay. So once I say 1 milliwatt, 3 volt, 2 volt, you divide and that is the maximum current drawable from the power supply. Okay. So now you have to assign how much here, how much here, how much here. The net current flowing from the power supply cannot exceed the given value for the given power density. And the last but not the least, after all, in a MOS transistors based any circuit, there are hardly, I mean though I am using RDs, but they are generally not there. We will like to have outputs driving next stages, and what will be the next stage input impedances? Capacitive. So they will be actually driving a capacitance. Okay. So when you give input change, how much the output takes time to change is called the slew rate. How fast, that is C dV by d0, how much current is available at the output for capacitor to charge or discharge is very crucial, because that decides the speed of this circuit or some way related to next stage how will it respond. So another term which will actually like, these are terms, why I am using same term, because this is what op-amp specs are. By the way, the circuit which we have just shown, which we will show now, is the first stage of op-amp. Okay. The first stage of op-amp is a difference diff-amp, so I am trying to use, but the final specs also are same for either op-amp or diff-amp. So I repeat, I am looking for power dissipation, I am looking for slew rate, I am looking for output swings, I am looking for ICMRs, and I am also looking for difference gain, and I am also looking for CMRR. There is another term which will come at particularly in the case of this, which is PSRR. We will see if power supply has some changes, what it influences to the end at the output. So we will also have another parameter, at least not in diff-amp, I will say I will put it finally to op-amp, which is identical stage. So I will solve all of them for op-amp. So PSRR, so that also is another important issue which you will have to address too. So these are the specifications. So normally what they will give you, okay, another thing which I did not say, the bandwidth, okay, which so far I am not putting capacitances, so I am as if thinking there is no, and then finally it will come from the bandwidth, and bandwidth is something to do with not only the RC time constants you get, but also on the FT value which the device is able to give you. And I repeatedly saying you that typically 10th is what you should be able to use safely if your device has to operate in proper mode of operations. Okay. Now that is something we will talk about in the frequency response part. Okay, that what is the bandwidth relations. We have already solved one small problem, you say bandwidth and these are some way related, because its first pole or dominant pole is essentially related to bandwidth. So if many cases we solve assuming this is the dominant pole, but in fact we will show you later, those who have done my earlier device course, I have used that method, zero time constant method, instead of using normal Bode's technique. We will show you that we can figure out at least quickly, if not very quickly what is the, which is the dominant pole. Okay, and if you get the dominant pole, that is your bandwidth. Okay. If you want to plot full Bode plot, that is all poles on zeros for stability purpose, you will have to go through all transfer functions, get all poles and zeros and plot it and find phase, which is another terminology which we will use later, how much is the phase margin. Okay, okay, so there are other parameters will come in op-amp, so wait for that. Till then we will only look for diff-amp characteristics, which is the first stage of an op-amp. Okay, so is that okay? So these are some issues we must address now, so that at the time of op-amp design I have in my mind what I am designing at. Okay, okay, let me look into common mode again. If you say Vx is Vy, okay, I join them, and there is a common mode signal which is V in Cm, sorry this is here, this is V in Cm, both sides same, so that is shown like this, RDs are this. So if you see it, it is essentially equivalently saying, and let us say this current source is not really ideal current source, okay, which is will never be actually, in reality there is nothing called ideal current source. So there will be some resistance associated with, and that resistance is RSS. Okay, so what I am saying is, so if I say equivalent circuit for AC, of course this DC is shown, but that is actually going to ground. I have RD by 2 parallel combination, and this is RS with signal of V in CM equivalently. This is a very simple amplifier. Which is this amplifier? This is a common source amplifier with source degeneration. Okay, though I have solved it, I inadvertently did not realize that I should not solve. So I kept solving, and then I realized that I have already solved this problem. So I need not resolve again, but just for the heck of it, the equivalent circuit is as shown here. This is the IRSS, this is IRD. IRD is minus IRSS because sign is taken down. Okay, in fact I should have taken sign up. Okay, so that would have been same, but does not matter, the voltages would have changed in the sign. Okay, then this would have been plus and that would have been minus, so it is saying the same. Okay, IRD, which is V0 by RD by 2. Okay, then Vs, which is the source voltage here, is IRS times RSS, but IRS is IRD, so this is this. IRSS is minus IRD, which is GM V1 plus current in this. You can see the current here plus current here must be equal to current here, which is IRS, which is minus IRD. So this method which we have earlier applied, I am just rewriting. You need not even rewrite, this is exactly what we did earlier. I am just, as I say inadvertently, I forgot that I had done, I keep solving things, then I realize why I am doing it, I have already done once. Okay, yes, is not taken. Normally what we will do in the most cases in diff amps or something, we will source and bulk we are connecting most cases specifically, but if not given, just GMB must be, you can even now add GMBs, it is not circuit, we already solved with GMB, so it is not that we cannot, but for the first take we always say the IC circuit will be allowing us, of course in a long channel devices we always did that, but in a short channel we cannot neglect GMB, which at the end after when I say if I scale down what I will get hurt and how will I get out of it. So that maybe after all that I say okay, from here to here what is my problem, which is your problem. My time it was very straightforward, I worked well, nothing went wrong, but now everything goes wrong, so how to get out of it. Okay, okay, so this analysis please, I mean those who wish to write figure it out, but I do not think there is nothing great I have done. Just see the last expression, all this is given by me earlier. So finally V0 by V in sim, which we call AVCM, is minus GM RO parallel RD by 2, RO into RD by 2 upon RD plus 2R. This is expression as we derived. Okay, and if we say RSS is much larger than GM, 1 upon GM, which will be, RSS is a current source output resistance, so it is very very large. So this may reduce to firstly you may say minus GM RD upon 2 1 plus GM RSS, or if you say this is also true then it is minus RD by 2 RSS. This is same thing what we derived for source degeneration, load resistance divided by source resistance, that is exactly what we get. However, why we actually derived this, because now we say that this AVCM is not 0, is that point clear? We are now saying at this at one end at least the voltage is RD by RSS, because RSS is not infinite. Okay, this is the most important part which I want to explain. RSS is finite, and therefore one must say that the V0 by V in CM will be finite, and it will be minus RD by, this is RD by 2, so this 2 is only coming because of that, so RD by 2 by RSS. This is essentially, we still assume that GM1 is GM2, RO1 is RO2 or something like this, but in case they are not there, which is what is why it need not be there, what is the cause? You are anyway doing technology course, you are doing other design course, what will be the cause in which two transistors may not be identical? What could cause it? Anyone? The reason why this mismatch occurs, a variety of reasons. The dopings on different transistors in the what we call channel implants are not correct, there is a spacer problem, there are many issues, boron depletion is another issue, and there is issue of different W bias actually during lithographies. Okay. So these are called mismatches, edge effects and mismatches. They will be there, do what you, how small they will be is what is important. We will prefer them to be almost identical but never identical, okay, as close as possible. If that happens, that the device, two devices, normally M1 M2 being so close, this difference will be very very small, but ideally this is only a statement. In real life the issues are different, there may not be only one diffam, there will be n diffams, each will have different variations. So in real life variations may cause on chip variation, chip to chip variation and wafer to wafer variations. So there are huge problems at the end of the day, it is called variability issues, and one has to take care in design now, variability issues. Okay, yeah, like threshold may vary plus minus 10%, then what do we do? Okay. Our assumption is Vt is constant, so everything is fine, W by L is constant, all that issues are, temperature is constant, all these issues are not true in real life. So at least we should look at least some of those variations and see what will it influence, okay, and that is why designers should know a priori. Okay. Is that okay? The issues are related to technology and they must be brought in your thinking, because at the end device will be fabricated on silicon, okay, or circuit will be fabricated on silicon, does not listen what you want to tell, okay, it does what it wants, and then you are left with thinking why it did the other way, okay, I wanted this, he is not doing, so what should I do now, that probably he will do what I wanted, that is some game you can play. Okay, so here is a case which is of relevance in real life. Let us say M1 M2 do not have identical characteristics, which is very true in fact, okay, so that then the Vx is not equal to Vy, okay, that is but for sure, because then if they are different they will not have the same values even if signal is common mode. If GMs are not same, how can you have same drops across the RDs, okay, and therefore firstly even RDs are not same, mean there is a delta RD goes with that, some plus some minus, so there are issues and issues, mismatches are very difficult to handle. Then of course the symmetry things should not be really used because they are not really symmetric essentially. We can, but I do not think we should use that. Then we just calculate the currents, as simple. I have one input common mode and let us say this voltage node is Vp. Now if we say so, IDS1 is GM1 V in CM Vp and IDS2 is GM2 V in CN minus Vp, then Vp from this solution can get GM1 plus GM2 by RSS 1 plus GM1 plus GM2 into RSS, and then Vx is something like this, where this one, yeah, sorry, if that is so that is true, I am sorry, I made, I think lower down मैंने correct कर, यहाँ नीचे लिख दिया मैंने, ऊपर शायद miss हुआ, is okay, fine, thank you. So if I find Vx and Vy, it is minus GM1 V in CM minus Vp into RD, वहाँ का यहाँ रखा मैंने, and then I solve, this is minus GM1 RD1 plus GM1 GM2 RSS into V in CM. Similarly I can calculate Vy, drop, nothing else, okay, drop across RD, okay. So I can calculate Vx and I can calculate Vy. What is the gain we are now looking for? That is what is called conversion of common mode into difference mode, because we are going to get a signal difference gain which is Vx minus Vi with reference to what? V in Cm, okay. So gain which is of more relevance is not just the way I showed you earlier, it is essentially this Vx minus Vy divided by V in Cm, that is the gain which is many times is called AVCM dash. Have you written down? Then I can show you the next slide, okay, fine. So if I, as I said, I am interested in the difference gain for common mode signal which is Vx minus Vy divided by and then I subtract Gm1 minus Gm2 delta this into V and Cm, and that then I define the gain is AVCM dash Dm. Is that clear? The new definition is AVCM dash Dm, which is Vx minus Vy by Vcm. So if I divide this here, I get Gm, then I define Gm1 minus Gm2 is delta Gm. Normally how much, ideally how much it will be? Delta Gm will be 0 if we say Gm1s are equal to Gm2s or whatever it is. And we also define a term Gm which is Gm1 plus Gm2. Sometimes they define half of it, I have defined as it is. So in some book if you say divide by 2, so 2 Gm will term appear in replacing this term. Okay. So that 2 sometimes if you see, don't think why मैं भूल गया नहीं, मैंने define ऐसा किया है, because I realized I figured it out in the book, they have used 2 I think, but I was solving and I defined something, so I kept it. So please remember this is my definition, generally it is half they will put it, okay. Average they say, but since I have not used it, my value may not show those 2's somewhere. And then we define the term AVDM divided by AVCM dash DM is essentially what we call as common mode rejection ratio. And if you now divide that, it can be figured out, it is 2 Gm, because Gmrd will cancel from there, so 2 Gm upon 2 delta Gm into 1 plus Gm RSS. So since we said we are one of the main feature of a DFAM is what did I say, it should be able to reject common mode. So if I want larger CMRRs, typically what is CMRR in dBs for a op amps which you use in the lab, typically like 741, how much is good? So 741 has at best 80 dBs, okay, 80 dBs kind. Normally we would prefer a good op amp is how much, 120 dB. So if you have to design a 120 dB op amp, you will figure it out, it will create hell of a problem for other parameters, particularly the phase margins, okay. So there is an issue how much CMRR I should be allowed, so that I should get the other performance also as good as I want. So that is the design issue, is that clear? CMRR is therefore kept flexible term, they say minimum CMRR should be 80 dB, okay. So you are not saying 120 dB, because otherwise you cannot design it. So issues are always clear, same way we will never say power supply, power dissipation should be so much, it is very difficult, it should not be more than so much, okay, or the slew rate should be at least this much, gain should be greater than so much, okay. These are the bars or the upper and lower bars we must decide, because then only design is possible. At any time you put rigid specs, nothing is designable, okay. So one cannot design a chip with very rigid specification, you must say more than, less than, whatever the bounds you can give, please give it, because then the designer has something to play on, okay. थोड़ा इसको बढ़ाओ, थोड़ा इसको नीचे करो, अभी दोनों ही गया तो फिर कहीं नहीं आएंगे ना, इसलिए that has to be understood. So if I want larger CMRR from this expression, as good the two transistors, better is CMRR, okay. Delta GM जितना कम होगा उतना CMRR ज़्यादा होगा, जितना ज़्यादा GM होगा, that is transistor have larger GM, means what is larger GM means, either it is driven by larger currents or they have large size transistors. Please take it, this large size word should be taken with a pinch of salt. Why? Because large size means large, generally lengths are very rarely changed, so it is the widths which are changed. If widths are changed, what will change? Capacitance, because capacitance are normally related proportional to W, all parasitics. So essentially you change the W by L, you will be actually talking about increase in capacity. In change the W to higher value, yeah, IDS will increase, everything will go nice, GM will be higher, but then the bandwidth will be affected, is that clear? And therefore one must not say increase W by L. But one catch I may say, I might have said also, any time you are worried about device to be in saturation, put larger W by Ls for given currents, okay. It will always enter saturation, think of it, what did they say, If I make particular current which is square law term, then see to it your W by Ls are much larger comparatively, then it will always remain in saturation. The other possibility of improving CMRR is to make this RSS very large, which is what we will try, because current source, as good a current source I will give for bias, that will be better. And if you can do this, obviously your CMRR will be larger. So now you can see there are parameters which you are governing CMRR. So if you change something somewhere to get other spec, this also will get affected, and therefore do not see CMRR as not a spec, it is a spec which is to great extent variable, greater than, oh I can't tolerate less than 80 dB, fair enough, okay, but do not say it has to be 80, it can be 85, 90 or whatever it is, okay. What typically 80 dB, all op amps, general purpose op amps at 80 dB, special op amps like LM323 or 321 or 8576 which is another device, they are CMRRs at 120 dB. Okay. They are low noise amplifiers and they specifically try to improve CMRRs, but their bandwidths are not very high. Okay. So there is an issue, that is what I keep saying, there are gains, different applications require different op amps or different amplifications and they have different specs. So you have to choose, if you are doing board design, then you have to choose from the data sheets which one you should fit. In chip we do not have a data sheet, we have to design, okay. So we actually solve it and figure out what is the, and another thing I keep saying, when I design something and I convert to layout, which is what one of the major output of any course of design, then the first thing we will do is we will, that layout which I have drawn for the poly for every region, then I will extract the circuit back from the layout and then I will re-simulate that circuit, and you will be surprised that whatever initially specs with which you have drawn the layout, they do not match, okay. So you have to redraw or re-simulate, change something, redraw it, re-extract till they are close by, assuming things are okay, because this layout is for a given technology rules which come, like you are working on 90 nano UMC 90 nanometer technology, so they have their layout extraction tool will actually follow them. So you are very close to foundry, is that clear? But even then there is no 100% guarantee that silicon will show you same performance, okay, but it will still be close to what you were looking for, is that clear? So at the end of the day, this is some turnarounds will be required. As many turnarounds is cheaper or costlier, larger the turnarounds, cost increases, because one fab you go through, you have spent already lakhs of rupees. Typical cost for a 90 nanometer process for a 2 mm by 2 mm chip or per mm square you can say is around 8 lakhs these days for academic this discounted price, okay. On a 12-inch wafers the cost is 2 mm, 1 mm per mm square is 8 lakhs on 90 and 65 nanometers. For 2.25, 0.35 it is 2.5 lakhs. So most of the designs which we do in the lab is only for the sake of money, because otherwise the money is too high, okay. Okay, DFAM with, now let us see DFAM designs or at least DFAM analysis once again, and there are 3 DFAM shown here, you can draw each of them. Instead of showing Vn by 2 and minus Vn by 2, I am showing you one together as Vn, that is the only difference from what I said earlier. Okay, the most important part which I did not say it, these are all CMOS DFAM, okay, अपने course का नाम CMOS है ना, इसलिए अब we will not use any N channels now, P channels other than together ही जाएंगे. So these are all CMOS DFAMs which probably are the ones which we will design. Whenever gate is connected to the drain, then it is called diode connected, okay. It's a P channel, the source is at the power supply side because you need negative supply VGS, so S has to be at higher voltage, so positive higher voltage, so that VGS is minus. Gate is connected to drain, so device acts like a actual diode. What is the difference between this diode, this is also a diode, and a normal diode? Do you know what is the difference? The diode has IV characteristic which is exponential, is that correct? So in all technologies in CMOS there is no real diode made, actually diode is this, okay. Size change करो, sometimes thicker oxide डालो, उसकी characteristics change कर सकते, but diode is this is how diodes are made. Is it okay? Last but not the least. So the first one is a diode connected load, which I just now said. This is standard n channel 2 devices which is forming a diffam pair which is biased through a ISS source, okay, and this is my input. The second one is these are current sources, you can bias it properly through some standard biasing system which we will show later, and this can remain as a constant current source, okay, it is called current source loads. Please remember these are p channel devices, and we are all the time feeling as if only n channel devices can be diffam pair. You can have inverse, you can have a p channel diffam pair, and you have n channel loads as well. Okay, the third and the foremost of all these are very specific ones and not often used in most of the op amps, okay. The advantage of these two are essentially, I did not draw it, okay, here also, these are double ended outputs, okay, these are double ended outputs, whereas the third one which is the most common diffam used in operational amplifier at the first stage is a single ended output stage which is shown here. The feature is very interesting here because here the two p channel gates are connected to one of the drain of this side, at times if driver is, you can do other side also, then the output will be the other end, there is nothing, they are symmetric, so it does not matter, but normally shown this everywhere, so I am also, you can as well do here and then take output from there, it is only question of mirror. Okay. The only thing which I did not say very specific here, this ISS there in most cases will come from either applying a bias such that this device always remain in current source mode, or actually it will be mirrored, the current will come from a current mirror. So if the gate of this is connected to current mirror gate, then same current which you are passing in that will pass in the this transistor, and this will act like a current bias circuits, okay. So it is either putting a bias, which sometimes good if you have a good reference bias voltage available like band gap reference, or then you do it normally with current mirrors, okay. This is what the single ended diffam essentially is, most popular diffam, which is, as I say, most popular simply because all first input stages of op amps are these, okay. But there, as I said other day, there is a fully differential diffams, okay, or fully differential op amps, then you do not need both outputs, okay, fully differential, and at that time this cannot be used, either of them will be used in that. So inputs to outputs, okay, is that called fully differential. So in those cases only you will require first two, otherwise most general op amps first stage is simple one single ended diffam. Now before we solve the case for the third one which is most important, quickly we will repeat. For the diode we already solved this, so diode connected load, the load resistance is essentially the GM parallel 1 upon GM parallel ROP. GM is normally very large compared to 1 upon RO, and therefore it is normally 1 by GMP, and therefore the gain is GMN by GMP, which is, now you see the difference, it is mu n by mu p into WL by N by WL by P, okay. So for a diode connected this, the load for diode connected loads, the gain of a diffam is already is, if mu n by mu p ratio is 2, so you have already got little extra gain out of using p channels, okay. Then what is the advantage if they are same, they could have been same, then this will have cancel, then the increase the ratio, I will have to increase more size of n channel compared to p side to form. Here already mu n by mu p ratio is giving additional boost. So still n channel device will be larger than p channel, is that okay? The current source load, the load is only ROP, then AV is GMRN, RON parallel ROP. The two ROs of the N channel and P channel at the output are parallel, so they are parallel. If they are equal, they will not be equal because of the mobilities, but many times they may be equal also because you may adjust sizes. Okay. Therefore, you may have GMN, RON parallel ROP. So these are standard difference gains for two of this, but what we are interested in at the end of the day is the third one, which is what we are going to design. Therefore, we should look into it little more carefully. Is that okay? These are trivials, standard this you can we have already done earlier these two, we are just repeating the results there again. Only difference in earlier case, and this is that here this N channel P channel device, so mu n by mu p will also have beta. So mu n is one time mu n Cox, the other is mu p Cox, so mu n by mu p ratio will appear, and that you must take care. Typically how much is the ratio of mu n by mu p in the actual semiconductors, silicon? I am not saying what kind, what is the typical value of mu n by mu p in a normal semiconductor bulk? 3, okay, it is almost 3, 480 to 1400 something, okay. However, in MOS transistors this can never be attained because the surface mobility is not as high as the bulk mobilities. So the best of ratios you may get 2.2, 2.3, and therefore most of our designs are for 2, because you may not get 2.3, okay. So we may say okay 2. So generally if you are not given any value, assume mu n by mu p as 2. I may specify beta n dash and beta p dash, so there is nothing you have to worry, but in case I do not specify, you can always use this as 2 because that is the most likely value. The best of mu n you may get is 600 centimeter square per volt second, and best of that you may get is 300 centimeter square per volt second for holes in most MOS technologies. In higher technology even it is worse. So it is becoming very difficult now to maintain even 2, okay, but that is the game we play enough, so that the interface states are very much in control, so that the mobility is roughly 2. These are called surface mobilities, these are not bulk mobilities, okay. Yeah, very good. नॉर्मल डायोड का IV कैरेक्टरिस्टिक्स ऐसा होता है फॉरवर्ड में, वो जो डायोड है IDS VDS वो स्क्वायर लॉ है, but if you adjust your sizes and VTs they look closer to that. So though they are not square laws, but they look similar, and therefore it is called diode, as such they are not diode, okay. Is that clear? Essentially this is the difference, this is a square law term, is that okay? But this is good enough in most characteristics requirement. The major reason is in either case the current here also is very small and here also is small, so diode blocking is still possible in the other case, therefore one says it is like a diode, okay. Okay. Let us look for the third one, which is the one which is of great interest to us, which is the first stage of op-amp, which is called current mirrored diffam, current sink, or current, it can be called, what is the difference between source and sink? Whenever current starts from power supply it is called sourced, whenever the current goes to the ground it is called sink, okay. So definition wise I just thought I should tell you it is actually sink source, current is sinking into the ground, okay. So in some books if you say sink, so I thought I must write that they may also call it sink source, still source of a current but it is called sink, okay. It is going to the ground, okay. Okay, so it is normally derived out of a transistor M5, and normally this VGG either has to be controlled or a mirror can be brought, mirror current can be brought to pass in this. Now we would like to first try to find out, before we do gains of this, quickly look into it. There are some voltages of interest. This is VGS3, please look at it. Acha, first you draw figure and then do not write this, write when I say, first draw the figure, that is most important. Have you drawn the figure first, then I will start talking and then you can write. I repeatedly saying that capital and small and everything should not be, unless stated otherwise by me, please do not worry too much about it. Okay. There is a voltage VGS3 for M3, there is a voltage gate to source voltage VGS4 for M4, both are p channel device. The gate is connected to the drain of M1 or drain of M3, both are drains. So that is our output 1, V out 1, which we are not very keen to know. Okay. What we are interested in, the output at this end, which is called the actual output of the amplifier. VG1 and VG2 are the input signals. Okay. Then this is VGS1, this is VGS2, or to say VG1 minus VG2 is the difference signal VID. VG1 is therefore VID by 2, VG2 is minus VID by, as we did earlier, equivalently saying. Then VGS1 is essentially this voltage minus VP, VG minus VP, VG minus VP. Now here is the catch, this is a DC current flowing in this ISS, okay, and normally it is a good current source whose output resistance RO5 is very very large. That is what the good current source is about. So I am postulate now, if it is an excellent current source, the change in Vp is 0, is that clear? Vp does not move, okay, or AC wise it is 0, delta Vp is 0 means AC. So essentially VGS1 is VG1 and VGS2 is VG2, okay. This is my statement. I may prove now that Vp has not moved anyway, okay. So that I did for earlier lemma, I am doing now for real circuit. The consumption now I am saying, please remember this is the statement I am making, and based on this statement I am going to make this statement to you that I can assume Vp to be grounded as far as AC is concerned. Is that clear? If this is not large, some current will flow, okay, that is the problem, okay. So we say right now RO5 is extremely large, okay, even if not very large is still doable, but at least we assume so, okay. Is that okay? Is that statement clear? Here is an equivalent circuit of the system. Please see it very, I had done it very intentionally, a different way of drawing the circuit. This may help you to appreciate what I am saying, okay. So look at the input side, one is VID by 2, other is minus VID by 2, and this is that common point where we say the output is, I mean this is grounded physically, signal, okay. Which is that point I am saying? I am actually saying from the ground, this to the ground, okay. इसका साइन देखो थोड़ा सा चेंज किया है मैंने, क्योंकि ये माइनस VID by 2 है, इसलिए उसको प्लस VID2 में ऊपर प्लस माइनस कर दिया मैंने, okay. If you see the M1 M2 transistors, then it is GM VID by 2 into parallel RO1 is the equivalent circuit for this. Please remember this is your Vp, okay. The other side is, please see the sign now, because of this VID sign, GM2 VID is shown down going from source to this. This is AC signal, please take it, this is AC signal across which there is a RO2, is that okay? So M1 M2 have an equivalent circuit, this is common point Vp, this is GM1 VID, this is GM VID. Same way if we go ahead for 3 and 4, 1 upon GM3 RO3. Now whichever, if it is diode this will dominate, if not this will dominate, GM4 RO4, okay. Now there is something which I am right now not showing here, another source, I will bring it little later, okay. But right now as if CIC, that is the equivalent IC. Now I will show you why I have not drawn then, and now I will show. Now the idea is something like this, if you see RO5 resistor, this side is ground, this is Vp. Now we say the current in VO1 by RO1 or VO2 by RO2 are very small. Why they are very small? Because ROs are very high, so we believe that those currents are extremely small. If that is so, this current and this current does pass through RO5 to the ground. Is that okay? This current and this current passes through RO5. Is that okay? Now the direction, if you see, it is GM VID by 2 goes like this, GM2 VID by 2 comes out of it. Okay. If you now say GM1s are very close to GM2 and that the RO5 is, what is the current through RO5? GM1 VID by 2 minus GM2 VID by 2, and that is very close to 0. Is that okay? In which case we may say the potential here is equal to potential here. So if the Vc is ground, Vp is equally grounded. Is that clear? So that delta Vp does not move by lemma is what I have used, but I now showed you through a circuit point of view that Vp remains constant, so no AC current, that voltage for AC is same as Vc. Okay, so this idea that in circuit how people use that, sometimes because they may not show you this, they may suddenly put a ground there. Okay, so you must know from where this theory has come that Vp can be treated for AC as ground. Is that point clear? Because in a book, if you see, they may not show all this, they may only show this and show ground, then you must not feel why this is grounded. This is how it is, looks to be grounded. Okay, this is what you say between the lines, what they do not write and what I can tell you from where they derive this. Okay, is that okay Surbhi? इसका एरो किधर है? इधर. इसका एरो किधर है? इधर. ये करंट सोर्सेस है ना, तो इसका पाथ तो यही है. एक इधर से जा रहा है, एक इधर से आ रहा है. इसमें से जाने वाला करंट सब्ट्रैक्शन है उसका, प्लस माइनस है, और यदि वो सेम है रफली, विच इज व्हाट आई एम अश्यूमिंग GM1s आर वेरी क्लोज टू GM2, देन वी से दिस देयर इज नो करंट इन दिस. एक फ्लोटिंग इसमें एक नीचे का पॉइंट यदि ग्राउंड पर, तो ऊपर भी ग्राउंड ही होता है, या जो पोटेंशियल नीचे है वही ऊपर होता है. एक रेजिस्टर लो, यहाँ जो पोटेंशियल है यदि इसमें करंट नहीं है तो ड्रॉप नहीं है ना, तो ये पोटेंशियल सेम होना चाहिए. दैट क्लियर? दैट्स व्हाई यू से Vp इज एज मच एज ग्राउंड. As much as is a very important one, it is not really ground, but as much as it is ground. Which, okay, the reason why I did it was because I figured out in the books they just draw circuits without telling you any great thing. So I just thought, so this is your input, okay, this is your GM1 VID1, this is GM2 VID, okay, RO1 parallel. Acha, okay, please just a minute. You can see if this is grounded, I can connect them. Is that correct? This is grounded, so I connect them. Okay, so if I connect them now there is some catchword is going on. Again this equivalent circuit is not accurate. अभी नीचे वाला आने वाला ज़्यादा accurate है, वो मैं आपको अभी दिखाऊंगा. अभी then what I did, I used this as a one कॉमन लाइन ग्राउंड. ओके, देन एक सर्किट इधर लिया और उसके आगे दूसरा सर्किट उसी ग्राउंड पे लगा दिया. दिस इज व्हाट नॉर्मली द फिगर इन द क्लास बुक्स विल बी दिस काइंड. दिस हैज कम फ्रॉम दिस. ओके, सो दिस इज ए टेक्निक विच आई शोड यू. गिवन ऐसा कुछ हो तो आप फाइनली कैसे लाते हैं, बुक्स हमेशा ये देते हैं. ओके, नाउ वी सी फ्रॉम हियर, if it is GM1 VID, okay, RO1 parallel this, of course it may, you may keep GM3 or not, it is up to you because the values will decide, but in real life we can keep them, whichever is not there will go away. Okay. Now this fact is most important. Have you drawn this circuit? Then I will explain. That is the issue which I am now telling. So the output of the first stage M1 M3 can be figured out by a current source of GMVID shunted by RO1 shunted by RO3 parallel GM3. Is that okay? Okay, have you drawn all of you? Okay, so look at it. This is the first stage, M1 M3 stage. I repeat, now you, should I put this figure? Okay. So I have figured out, I first solved this M1 M3 and got V out 1. But now look at this V out 1, where is it get connected? to the gate here. This voltage is same as this voltage. For AC this is ground, okay. So this voltage is same as this voltage, they are connected all through, is that correct? And now there is an issue started, and that is what you were saying, वो छोड़ा क्यों, अब मैं आगे दिखाता हूँ. Now you can see the output at this second stage, which is M2 M4 stage. One input is coming from this VID by 2 minus VID by 2, but there is another input coming from here, वहाँ VGS है, M4 में भी एक इनपुट आया है, दिख रहा है आपको VGS4 जो AC है, बिकॉज ये AC है आउटपुट जो वहाँ कनेक्ट होके आया है. So when I see output, now I see I have two inputs, one at M4 and the other at M1, M2. So I must now actually superpose the two, I must get the voltage due to the VGS4 and also should get output due to VGS, VG2 or VID by 2. So I need both sources to be now used in evaluating the V out. That is the interesting part, is that clear? जो कि बहुत obvious नहीं है, इसलिए मैंने वो पहले बार नहीं दिखाया. Is that clear to you why the term which I am now showing? There are two sources for this output. One is if I give input here, if I give input here. Okay, so there are two transistors are receiving inputs now. Okay, so what is the method I use? Initially do not treat this, treat with this, next time treat this, or output due to VGS4 and output due to VG2 or VID by 2, I will add them, superpose them to get my V out. This is the technique which all of us directly or indirectly use. Okay, so I have shown you how from where this method has been chosen, is that clear? If I do not connect this, this issue will never appear, is that clear to you? But as I connected to make it single ended, the first time I realized that the output of the first stage is input to one of the transistors of the second stage, is that clear? And that must be now taken care in solving. Okay, is that okay? So if I do that, which is what is relevant for in my opinion, now you can see what Raj was saying I am hiding. Since VO1 is VGS4, is that okay? VO1 is VGS4. So apart from the first M2 के कारण जो आउटपुट है वो तो GM2 VID by 2 सोर्स से आ रहा है. What is the resistance it is going to see? RO2 parallel ऊपर का RO4 1 upon M4. But the same resistance is also getting additional voltage, because the output will still remain same, resistance will remain same because M2 M4 are still same, but there is an additional current source sitting here which is because of M4, which is GM4 into VGS4, is that clear? There is an additional current source which is GM4 VGS4 and there is one normally GM2 VGS Vin is already there. So now you have two currents. The only interesting part there is AC wise both are, एक ऊपर लाने की कोशिश कर रहा है, एक नीचे से ऊपर जाने की कोशिश कर रहा है, and that is why their signals are, current sources are shown opposite, is that clear? This is the crux of diffam outputs, is that clear? If I do not show this, then I am making a great error. Okay, this is the reason why you see a gains as shown in the books, because but as I say most books do not show this kind of equivalence. So I thought maybe this is a high time that I show you that from where they are getting those expressions. Is that point clear to you? There is a transistor M4 is also receiving AC input, and M2 you are actually putting an AC input. Okay, both contributes to the output of the second stage. Okay, they must be superposed. The problem was that one is pushing the, because of VGS is a p channel device, the other is n channel device, so the direction is opposite, so they are as, but one of them is minus sign, so probably they may still add physically in numbers. Is that okay? Okay, last quickly we will finish up, or maybe we will stop here, we will show you next time the gains. So is that equivalent circuit? Please now remember, this is the real equivalent circuit of a single stage DFAM. Is that okay? This is the equivalent circuit of single stage DFAM. Okay. Now calculation are very easy, output is here, substitute back here in that and calculate V out finally, which is then V out by VGS, VID by 2 will get us, or VID will get us the difference gain. Is that clear? So next time.